An interesting talk on optimization, getting 60 FPS on mobile by Avinash Pandey and Nikolai. Avinash has been in the gaming industry from 2008, and Nikolai is a graphics programmer, so excited about the talk.
Okay, over to you. All right, thank you. Thanks for the intro. I'll just switch it off. Okay, I'm going to use this one. All right, more than expected crowd. I was expecting this room to be fully empty, but we have 5 people. It seems like everybody's game is running at 60 FPS already. So hopefully, players are going to have great experience coming soon. But we'll still talk about this topic, which is very important, at least for us. And the reason why we chose this topic is recently we have seen a lot of multiplayer games struggling with this. Even bigger studios have a lot of problem. And if you are working on a game which is very demanding in terms of graphics, like open world game, any MMO or battle royale, this becomes really complex. So we'll try to make it engine agnostic, but since we use Unity, so a lot of topics would be around Unity engine, but we'll stick around, and if you want to talk about general techniques, we are happy to share. So, I'm Avinash, Nikolai is here. I have built a bunch of games before, only been in mobile space, so that's why this topic is like very, very close to me. Nikolai, on the other hand, has a lot of experience on PC and console as well. So if you guys have questions related to that, just feel free to ask him. Okay, so the game we are working on at Lila Games is Project Black. It's an extraction shooter game. So the technical complexity of this game is similar to any battle royale or open world game. So the techniques we'll talk about applies to different genres as well. So our focus is going to be just focusing on starting with our learnings and general practices, not going too deep on that because a lot of resources are already available on different game engines. But on the second part, when Nikolai comes on the stage, he's going to talk about some complex techniques and some custom solutions which we use. I would recommend always choose solutions which is needed for your game and treat some of those topics as educational so that you should be aware of them, but doesn't mean a game needs all of those techniques. So moving forward, this is my personal philosophy about optimization. So optimization is a balance between ambition and reality. So whenever you are working on a game, generally teams get very ambitious. Because team is not only one person. There are artists, there are designers, engineers, and everybody wants a beautiful looking game. So the scope gets escalated really fast. So you have to make sure that your ambition is checked with reality. What I mean by reality is you should be aware of the target platform you are targeting. So if you are a mobile game, you want to target low-end devices, make sure you have planned for it. So always have an ambition, but check it with reality of your target platform, of your capabilities. We are being very ambitious. On the other hand, that's why this talk will have some topics. We'll be like, why are these guys doing this? Because we really want to make a beautiful game. So we are very ambitious in terms of design, and we are also very ambitious in terms of making our game look good and feel good. Because this is 2024, we'll launch next year, and players also demand like, hey, now the quality of the games are better. So as much as we can push on that direction. So first I'll cover the basics, but I'll move fast because these things are already available. Whenever you are in a phase of optimization, I would recommend read the instructions and resources of your game engine carefully again, even though you might be aware of it. But once you go through the same resource again, you get a lot of ideas. So do that again. If you have done it like twice, do it thrice. Optimization is not a one solution fit all. So there might be a lot of check boxes you can check which individually do well. You might see a sample, hey, I did this and my FPS improved by 10. But if you are already optimized and the bottleneck for your game might be very different. So you will have to do things which is very specific to your game. The most important thing from the start, if you're working on a complex game, is freeze your design scope and set your visual benchmarks. So this is something not easy to get into. Like, we were thinking, hey, we are very, very strict about our pipeline, the scope, but even we escalated a lot. So no, this is one of the mistakes you might end up doing. So just freeze your visual benchmarks. I'll talk about how you can do that. So this is again another quote I always feel works for us or for many teams is best optimization is no need for optimization. So if you come across a complex problem, don't try to immediately solve it by tech. First see if that problem needs to exist in your game. So if not, just remove it, problem solved. The best optimization already happened because you don't have to do it. All right, our learnings: optimize major hitters first. So when you start profiling your game, you will see a lot of areas, and some areas might be very, very complex to optimize. So let's say if you want to optimize your gameplay code, just to get 1 millisecond or couple of, even lesser than 1 millisecond might need a lot of refactoring, lot of code changes. So prioritize what are the major hitters and optimize those first, and deprioritize things which might be very complex. Build optimized assets. So from our experience, despite doing a lot of tech, most of optimization in our game came from just making optimized assets, which I'll show in next slides. Be true to your budget. So whatever budget you decide, I'll also share our budget. Just always make sure don't go beyond it. This is another mistake which studios do. Only expand certain areas when you have technical expertise of it. So let's say if you want to increase poly budget of your game, hey, now I want to render 500,000 triangles on the screen. Make sure you have technical capabilities to back it up. Just some trade-off in different locations. So for example, this is the water in our game. It has no depth, so we don't do depth because depth is more complex. It needs depth texture, more performance intensive. It just has transparency and specularity, and it looks good. So decide what trade-off you want to do in graphics and where else you can put that trade-off so that game ends up looking good. So here, this is before and after image of one of the shots of our game. On the left, these assets were already optimized from the art side. So here we have 800K triangles, 1900 batches. On the right hand side, almost looking the same, we took a pass, very basic pass, and it's almost like 100% more performant than the left side. And the basic techniques we used is just LOD changes, art optimizations, and just including some occluders in the game. This is a house. So on the left, you see 16,000 triangles. House looks pretty good. This was again from the art side, it was already optimized. But then we again took one more pass and got rid of more than 50% geometry. And on the 6,000 triangles, we get the same house. So budget and rendering optimizations. So this is a budget which I have written works best as of now. But mobiles are getting stronger. So just make sure what is the complexity. But for a mobile, 100 to 200 tries per frame is a very safe area. Make sure the dynamic geometry is also not too much. So around 50K dynamic geometry, you'll be in safe space. We strictly do single pass rendering. What it means is no pre-pass. Entire scene is rendered in a single pass. So except there is, we also introduce Bloom, which is multi-pass, but we make sure that the entire rendering is single pass, especially for mobile. Watch out for transparent assets. So this is again a general practice. Everybody would recommend, and foliage and VFX is the one which can escalate this. Again, if you have really good team, people can make really nice VFX, but just make sure that they are optimized. For example, if you are doing smoke, just make sure 2-3 chords, if you can just achieve the entire smoke effect with just those. You will have to go crazy in some of those effects. And when you build some tech for it, make sure you have ability to enable, disable those things. So we have lots of post-processing effects, which I'll show. But we also have ability to disable them on different devices. So that's also an important thing you would want to build for your game. So here, this shot is no post-processing, just 3D assets in the game. MIP fog. So we built our own fog, MIP fog. It looks pretty good. It's just you get a nice gradient. On the next one, we do tone mapping and color grading. So you can see the difference between first, second, third. And then we also have even more post-processing. We have bloom, we have chromatic aberration. So all of this put together makes it look really great. But this we only do for the high-end devices. For the low-end device, actually, we tone it down and we disable some of these effects. Project Black, this is the high-level rendering stack, which Nikolai will go more in detail. So we have custom shader graph. So we have modified Unity shader graph to generate shader descriptions for us, which then goes to more complex operations to generate lighting and materials. So at then, basically, we have control over shader generation. Shader graph is very powerful for artists and technical artists. Anybody can author the shader, but we have fine control over how many features gets enabled, disabled, and also control over shaders, because shaders can escalate really fast. We have built a custom render pipeline. So I'm not sure in Unreal how do you do that, but in Unity, both URP and SDRP are based out of based out of a render pipeline, which you can then build your own render pipeline on top of it. The reason we did that is we wanted very fine control over where we spend time. So generally, all the render pipelines of game engines are general purpose, and they might have some very small overheads like across the board, which might take few milliseconds from you. Do this only if you have technical capabilities, because this will break some features of your game, and then if you download some assets from SS stores or third-party assets, they will not work. So do it only when needed. So you might get a couple of milliseconds from there. We have built our own cached shadow system. So shadows are very expensive on mobile. What this does is we cache static shadows and then draw dynamic shadows on top of them, and that's it. We don't draw shadows every frame. Whenever camera moves to a certain distance, then we need to redraw it. So this brings great performance, and also you can have shadows on mobile. Custom terrain system. Terrains could be a little bit performance intensive. And for our game, since it's an open world, terrain had to look really nice. So we do custom splatting process, custom shaders, and terrain looks really cool. But there are some third-party tools as well, but it could get very expensive. Just make sure you look at what terrain shaders you are using. We do a lot of post-processing, but all of them are very, very cheap. Maybe Nikolai can just hint a little bit how do we make them cheaper. But we do tone mapping, color grading, which I think everybody should do. It's very, very cheap. Can be done in a single pass. Vignetting, chromatic aberration. Bloom is the only one which needs multiple pass and could be very expensive. So maybe you don't want to touch that, especially for the mobile game. These are my last slides. So CPU and GPU uses. This is the recommended budget. Always make sure you don't utilize CPU or GPU more than 60 to 70%. So when people say my game is running at 60 FPS, make sure it's below, the usage is below 60, 70%. So you should be running at 90 FPS to support 60 FPS. Otherwise your device will hit and you will have a lot of issues. You will not be able to support longer game sessions. And at different stages, you might have either you are CPU bound or GPU bound, and that's where the trade-off comes in picture. So let's say if you're GPU bound, what you can do, you can take some overhead of GPU and put it in CPU. What I mean by that, let's say you can use occlusion culling, where it will reduce your GPU load, but it will take up some CPU time. So those techniques you can use. If you are CPU bound on the other hand, which is a more dire situation to be in, then there are techniques like GPU skinning, GPU culling. Even physics can be run on GPU to offload CPU. So there is this game called Playbook. You can check out. They do a lot of fluid simulations. That is actually done on GPU. If you are doing that on the CPU, your game will die. So these trade-offs are really important to know. Especially for mobile game, don't choose native resolutions. Even a 10,000 rupees phone in India would have very high resolution. So just choose a resolution which works for you, looks really good. Especially for the low-end devices, have ability to enable, disable everything which is needed. So just make sure your game works on low-end devices, looks decent, but don't have like very high expectations of it. And that's why a lot of games don't perform well on low-end devices, because people have not thought about those trade-offs. Rely more on the arts rather than technical feature. So anything you can achieve through making a good art asset, try to do that on mobile devices than any technical requirements. One trick, if your game is third person or first person, make sure your character looks good rather than the environment and everything else. So generally people look at your character and play the game. So even on low-end devices, if you do good job on your character, rest of things are flat, fine. It still gives you very good gameplay feel. This is the resolution which we generally target for low-end devices, 480p to 540p. So just choose a lower resolution which just looks good. If you take a screenshot, it will look bad, but just make sure it looks good on device, you'll be fine. Especially for fragment-bound situations of your game. Shader complexity, on simple words, keep it very minimal. Avoid texture reads. Avoid branching. Branching could be complex if you are doing a lot of complex operations. So make sure your shader already has all the data available to it. And then I would recommend don't do post-processing, but if you choose to do it, do bare minimum ones like tone mapping, color grading, and maybe color fog. LOD bias, a lot of games use it, but if you do good job in optimizing your art assets, you don't need LOD bias. Lower texture resolutions. goes unsaid. Main thread optimization is one of the most challenging things towards the end, because now you are touching gameplay logic, which has to be same on all devices. Graphics can be different, but gameplay has to be same. So it could get really complicated. But then you can take off some rendering overhead from your CPU. That's where you can have some more saving there. And one more thing for low-end devices is just try to achieve 30 FPS constant, so that smooth gameplay on 30 FPS is better than a flickering gameplay of 30, 40, 45. One more trick about resolution: just read Android's documentation. Not every device supports all the resolutions. So resolution, the target frame rate is divisor of the resolution of your the frame rate of your screen. So if you are running at 90 FPS, your game might not be able to support, let's say, 50 FPS, or those frame rates. It has to be divisor of that frame rate. So if your game is not running at that, you are like, why is that happening? Just read how the frame rates actually work on mobile devices. This is something which we experimented with. So mobile devices have multiple cores, and make sure the main thread is always running on the performing core. Game engines already do that for you, but sometimes we have seen, again, a deeper topic, you can change thread affinity and you can make use of more cores on the mobile devices. Again, experiment, read about it. This is a screenshot from Perfetto. The Perfetto is an Android profiling tool. It shows all the cores and how your work gets distributed across those. Something to actually very interesting to read about. Last slide, this is our game. On the top is iPhone 12, high-end device, and on bottom is Redmi 13C, which is 10,000 rupee phone. A lot of features disabled, but I think this is not too bad. So make sure you have the ability to turn off a lot of features. With this, that's it from my side. I will welcome Nikolai, who is going to talk about deeper topics, and we are very tightly on the time budget. So if you have questions, we'll be around for answering those. Nikolai.
All right. Hello, everyone. Apologies in advance. This is the first time I've ever done something like this, so apologies if I stumble a lot in the process. So let's move on. We don't really have much time already. So Project Black. So Project Black is a Unity project built in Unity engine, and we utilize scriptable render pipelines for driving the rendering of it. We target Vulkan, and as a fallback, OpenGL ES 3.2 on Android and Metal on iOS. We try to use some GPU compute shaders when possible, especially for GPU resident only data that does not need to travel between CPU and GPU. That saves quite a lot of CPU performance. Initially used Universal Render Pipeline, a heavily modified URP, but then transitioned to our own custom render pipeline for simplicity. For regarding the regular shaders, the regular vertex fragment shaders, we mostly use a shader graph because it's a very controlled environment and it's very easy to use for everyone. Not everyone really likes to code in a shell cell directly. So just as a quick recap of how rendering was in Unity back in the olden days. So Unity had only one render pipeline that was hidden behind the C++, now commonly referred as built-in render pipeline. So it's a pretty defined render pipeline, and it's fairly customizable, so you can write your shaders directly, and you can inject custom rendering commands into it as well through command buffers. But nothing is like ultimately it's pretty subpar in the long run because it's still very, very much fixed with very fixed lighting models. You can't really customize them. You can't really customize how Unity renders those. It's also a pretty old pipeline with very questionable decisions that don't really make sense nowadays. So, for example, the multipass shadow rendering. So that was pretty alright, like in the PlayStation 3 days when you had very limited memory but didn't have a lot of pressure on the bandwidth. But now it's the inverse. You have quite a lot of memory, but you don't really have much bandwidth. And the rest of the things like the grab paths that you can erroneously use and tank your performance, Unity 4.x era image effects, and so on. And modifying the shaders themselves is also very difficult because the internal shader library is installed in the Unity engine directory, so you either have to modify that or you have to make a fork of it, import it into your project, and make sure that all of your shaders use that. So that's pretty cumbersome. So how does Unity solve this? Right. Oh, I'm sorry. So how does Unity solve this? It solves this with the SRP API. So what is the SRP API? It's a C# API in a Unity engine that you can use to describe and drive your render pipeline. And Unity will use that to render your game. So now it's going to be fully the responsibility of the user to author how Unity manages its resources, render targets, how it binds it and renders to it, and it's also the responsibility of the user to author shaders themselves. So as an example, HDRP and URP are both SRPs that are made through the SRP C# API. So that's already a major improvement because this is a monumental increase in transparency, so you can see directly how the game actually renders on both the CPU and the GPU. You can inspect it, you can modify it because like the C# code is available to you as a package. And this also allows you to customize them very, very heavily on the GPU itself as well, because all the shader source is readily available to you. So even despite it being a C# API, it's still much faster usually than the built-in C++ render pipeline, in part because Unity also introduced a lot of performance improvements to the rendering that's only available to the C# API. A lot of modern stuff goes directly there. So this is still a pretty high-level API. You're not working with Metal or Vulkan or OpenGLES directly. You're just working through the high-level abstractions. And this is portable enough. This is pretty comfortable to work with, but at the same time, this is sometimes not low-level enough for some very nuanced features, and we can get to that later. You'll see some instances of it. So regarding our own project, we had a pretty clear vision of what we wanted to do with SRP. We wanted to constrain ourselves greatly, so we did not want to make a very wide game with a lot of different features. No, we wanted to actually constrain ourselves and make our render pipeline as simple as possible, because that's already a great optimization. We don't have to transfer memory a lot of times. We don't have complex memory operations and all, and that's a pain on mobile. So we render nearly everything in just one pass. Like the main scene rendering in our game is strictly one pass, and yeah, this by itself just reduces bandwidth by a lot and increases performance for opaques and stuff, and it also allows us to do cheap MSAA, because in such a setup we don't really have to restore any textures afterwards. We can just resolve the MSAA on the tile memory itself and just store the resolved texture data to the main chip memory. And we also wanted to use as much of the built-in SRP API and the SRP library as much as possible, particularly with things like volume system. So you Unreal Engine folks probably know that you use that constantly. Well, this is the same thing in Unity. You just define a volume that that blends parameters based on the camera position, and that is used to drive various effects, post-processing, and rendering configurations. And ultimately, we wanted to call the edit cheap, so pretty contradicting things in the long term. But yeah, the resources are actually there. The techniques are actually there. We can implement a pretty good techniques that look good with our game, but we'll just need to fix a lot of things in the process, and you'll see some of those. So regarding the shaders, well, yeah, we have very controlled environment. We have an abstraction API for surface shaders. Those are not like surface shaders that Unity has, but it's a GPU library. that allows us to just fill up the surface description structs on the shaders themselves, but the shaders themselves never actually perform any complex operation later down the line, and that already gives a lot of constraint and does not expose a lot of low-level stuff to us. And this library is used for both SLSL shaders and shader graph shaded through our custom node, so it's pretty comfy all the way. So our game is mainly HDR rendered, so that's not referring to the HDR displays in the mobiles, that's referring to having your scene rendering performed into a render texture with HDR color management, so your colors are not really clumped. This is actually free nowadays, so you don't spare any bandwidth cost or memory usage with that. Most of the virtually all modern GPUs support these low bit formats, and there's really no issue with that. So that drastically improves our quality and simplifies our rendering, because we can just do everything in linear, and stuff like post-processing and like blurs and other kernels behave now correctly because we actually blur the raw HDR data and not the clamped LDR data. But in order to make it work, we need post-processing, and especially we need tone mapping and color grading to map all that HDR data back into presentable sRGB LDR data. So most of our post effects are a single pass in an Uber shader, so like color grading and tone mapping and so on. But we had to make bloom as a separate post effect that can be toggled on and off, and it's also HDR, so it does not smear everything. So we can just constrain it to very high brightness pixels and leave everything out of the way. So it's not like PlayStation 2 LDR bloom that we had back in the day. So yeah, it turns out pretty simple from the high level. So it's just GPU skinning and particle simulations, then shadow map updates, then the main scene rendering where everything main things happen, and then just scene post-processing and UI draws, also just all in one pass, except bloom. So, and yeah, because this is such as a constraint in simple pipeline, we do get a lot of benefits, especially with cheap MSAA and the stuff. But like, in order to make this single pass rendering work, we also have to ensure that we render things correctly, especially with like opaque, alpha tested, and transparent effects, transparent objects. So like, we have to ensure that we use alpha tests very, very sparingly, because alpha tests, even if the shader doesn't use them ultimately, if the instruction still exists there, it disables early Z, and in turn it disables HSR. And we really need to maintain HSR for as much objects, as much fragments as possible. It's like SSR is really the only option that we have left when we're rendering in single pass. Like, no, we can't do anything more. Dev prepass is not an option as well. Like, it's faster than SSR, but doing just a dev prepass is very taxing, and it removes our ability to do MSAA efficiently. So yeah, initially used a very modified URP with all of our features initially implemented in there, but we transitioned to a custom render pipeline down the line. And it was fairly easy because we already had like a separate shader library for all of our stuff, and we just had to transition that to our own SRP. So lighting. Our lighting is physically based. So it's just a regular limberation for diffuse and simplified GGX approximation for specular. It's energy conserving, so that's a big quality boost as well, and easier to control for the artists. We have different SSS approximation through ROP diffuse, and we also have character shaders that can sharpen the lighting to create a kind of a tune effect. So it's like, not a cell shader, but it's a very sharpened diffuse. So that gives a lot of quality and simplicity. For ambient lighting, we use the regular light maps and spherical harmonics in the light probes. And for quality reasons and like to experiment and compare, all of these features are defined as configuration files for our entire shader library, so we can swap them around and compare them to each other just to compare with the qualities. For example, we have like a very high-end console like Disney Barely Diffuse and full GGX with full resolve GGX for ambient lighting, and we compare against that just to maintain quality, because we really want physically based. Physically based is awesome. But, well, here comes the first trouble. Ambient specular. That was really, really difficult. Like, now that we are in physically based land, we want like very accurate specular, and traditionally that's done through reflection probes, but like we can't just use them. Like we can't leave just one skybox affecting all the specular lighting, like because we have indoors, we have very drastically varying lighting conditions, and specular is just not going to match there. That's going to be very, very visible. So that's a no-go. So reflection probes, we can probably use reflection probes, but we are actually heavily limited. So we can't rotate reflection probes, like we can't like apply them on a per pixel level. They are applied on a per object level. We can't do blending. We can't do anything of that regarding that, and that limits us considerably, and that makes situations actually worse in the long term. And this is much, much worse with metals, because metals can only see specular. Metals do not get the diffuse component. So all the metals now look instantly much, much worse. So like one of the things that we wanted like initially to use is to use some kind of renormalization, like to use light map data to tint and modify the energy of the reflection probes, so like in God of War 2019. But we can't really do that because we can't upload any custom reflection probe data on a per object basis. So that's one of the things that actually limits us with the SRPs not being low level enough. So what we do, we just reinterpret diffuse light map data as specular. So that's initially that's a very wrong thing to do in like at first sight, but this actually gives us much better quality because the light map data is much more dense and it exists on a per pixel level, and that gives us already like per pixel application and much better transitions and better lighting consistency. So that worked out surprisingly well, and like it's not a new technique. People wanted to use light maps for lighting specular for quite a long time, and there are some examples of that as well. This breaks for pretty smooth objects, but like the saving grace is that our game art is pretty rough all around, but we do have fallbacks to reflection probes on certain materials. And we also wanted to have shadows. We wanted to have true shadow maps for attenuating the lighting, because that's pretty high quality. It gives the impression of a pretty high quality game and high quality shading. Yeah, that actually is pretty expensive. Because like we have to render shadow maps through Unity, and Unity is not exactly fast with that, and like we can probably just reduce the distance of the shadow maps, but we also want shadows like to be very, very in a distance. So the shadow maps have to scale at distance, and that's pretty challenging. So we just wrote our own custom shadow map system that we call baked shadow map cascades. So it's like a cascaded system. But what we do is that we have several cascades centered around the player, and those only store static shadow map data. That only gets regenerated when the player moves far enough from the last capture position. And all the dynamic objects that we don't have a lot of dynamic objects just get drawn on top of it to compose the final shadow maps. So overall, a tremendous improvement in CPU and GPU performance. We saved quite a lot of performance with that. Because we used shadows, we did need to have some hacks for SSS because our SSS is just wrapped diffuse, and that means that self-shadowing artifacts can become really, really apparent. So we just introduced a custom bias for these shaders to offset the sampling position, but we do have to be careful with that and not overdo it because this can actually cause some light leaking, but it was not a problem for us. So for fog, we have very sparse locations. We can see really, really far into the distance, so we needed some kind of fog. But Unity's default built-in fog is pretty subpar. So it's monochromatic, so it's just a single color in every direction. So you can tweak your fog to look pretty good in one direction, but it always almost breaks when you look in the other direction, and that's very, very apparent. And it's also not really optimal because it has multiple confusing scatter calculation parameters, modes, they are free and plus disabled, and each single one of them is its own shader variant, and we do not really want that. We want to save some memory on our shader variants. So we implemented a custom fog solution based on Uncharted 4's MIP fog. So we drive our fog color through an artist-authored HDR cube map. And that already gives a lot of improvements because the fog is not monochromatic anymore. It varies by direction. And this also allows you to approximate stuff like atmospheric scattering by just baking it into there. And we just have one scattering method for computing it through Beer-Lambert's law. That's a good name. And we also evaluate it on the vertex shader completely in order to save performance. The fog is not contrast enough to make interpolation artifacts apparent. So this is our scene without fog, and this is with our MIP fog applied. So already a drastic improvement to the distant scenery, and you can see that it varies by the direction you're looking into. So, and last but not least, and not necessarily rendering related, but PSO pre-warming. So that was a very big issue for us. So just as a short pretense. So when we target Vulkan and Metal, it's no longer enough to just use shaders to draw things. You actually have to use a pipeline state object. So this is the thing that actually gets used when you draw things. And this doesn't incorporate just the shader itself. It also incorporates what mesh data you're using, what textures you're rendering to, what state of the fixed pipeline you have, and so on. And this makes permutations just explode, and it takes time to compile these things. So this usually manifests in that when you're trying to draw something new, you get a very big hitch that's just compiling this PSO. So it's even worse than with just regular shaders that we had in stuff like OpenGLES. So just a small nitpick, most of the games call those shader compilation, but that's not really shader compilation, that's actually PSO compilation. That's not confusing at all. So yeah, we have a problem, we have to do something with it. And the things are pretty dire with Unity right now. So Unity has a Vulkan PSO cache on OneDrive, so that's pretty good, but we can't rely on that because the first launch of the game is going to be stuttery, and we just can't afford that for new players. And this cache also becomes invalid if your driver gets, or your driver or firmware gets updated, or you update your shaders. We can't use shader variant collections. So Unity has a feature called shader variance collection, where you can store all the various shaders and their permutations to a collection and just pre-warm that. But that's not enough to pre-warm a PSO. You will still get invalid PSOs, and you will still get stutter. But there's a new API called Graphic State Collection that landed in Unity 6 that tackles that, but problem is we're not on Unity 6, we are on 2022.3. And it's actually pretty subpar so far because it only captures the PSO states for the currently active API for the current device. So you may capture it on one device, but it becomes invalid on the other device to pre-warm. You will still get stutters. And we can't modify the Unity, we don't have source code access. And we can't really drop Vulkan and Metal at all. We really need to support them. So we just implemented a custom solution in managed C# code. So what we do, we scan the system, all the scenes for all the renderers, and we collect all the renderer-specific and material-specific data that can be used to construct the PSO. So stuff like shaders, the local keywords, the mesh data that they use, and like int floats because they can influence the state of the fixed pipeline. We store that into asset with deduplicated entries, and on runtime we just perform a dry run of our SRP code to pre-warm that data by reconstructing it and the meshes that they use. That's already a drastic improvement. We reduced almost all of our hitches, and it also works automatically with the Vulkan PSO. So, like for example, the first dry run of game when we perform shaders takes 30 seconds, and then later loading all that data back takes just 4 seconds with the same pre-warm code. We do have to be careful because some data, we have to be careful with how we store data and reconstruct it, because even a slight error can create a different PSO that's not going to be useful and will not pre-warm any actual useful PSO. So yeah, that's about it.
I said this was a longer talk, but a lot of complex topics discussed here. But make sure you are aware of them, but they might not apply to your game. So hopefully this was helpful for you. Any questions?
So you said in your slide that there was a topic section called CPU GPU bound situation,
Yeah.
where you said that if one of these units are getting overhead, then you shift the workload to the other.
Yeah.
Right? So you've written that code which does this, which dynamically shifts the load to the other unit.
No. So what I meant by that is, if you are aware, let's say that you are GPU bound, but you have bandwidth on the CPU, then you can use features like occlusion culling, which then reduces your GPU load, because you are occluding, you are already doing heavy operations on your CPU to just limit the geometry which you are going to render on GPU. So you spent more CPU, but to save the GPU. So
Right,
this is
that is in the budgeting, right? Like that's not dynamic runtime.
No, not runtime. This is a decision. This is while profiling. If you find yourself in a situation where you are bound by either of them, then some trade-offs, like spend some time from GPU and some time from CPU to just balance it out.
Got it. I have one more question. So this is about the cached shadows system. So can you just explain that? Is it like a normal shadow map?
Yeah, it's a regular
For static
normal.
objects.
Yeah, it's a regular normal shadow map, but we just render it in a custom way to not re-render a lot of objects. So games like Call of Duty use that extensively, and like this is also a feature in stuff like HDRP in Unity.
Got it. Okay. I'll ask question more about that afterwards.
All right,
That's
sure.
okay. Yeah.
Good morning. Can I show you something? Like at a certain time in a frame, how many vertices to match the performance? How many your environment, how many count of the vertices are required?
Oh, so in one of the slides I had shared, it totally depends on your game, but the safest range is 100,000 to 250,000, which we have found for our game.
Like that, can you show it?
Show what?
Just
You are asking about the...
yes, the maximum vertices count.
Where?
Like tries vertices.
Oh yeah, this one, tries.
Yes.
Yeah, this one, yes.
Yes.
So it's like 100K, right?
So
This
it
one.
is in perfect range right now.
Yeah, it is in good range. But your complexity might be somewhere else if you are still struggling
No,
with
the main struggle is hairs.
Okay.
So how you manage the hairs in?
So we can talk about more in detail after this.
Thank you.
Yeah. Any more questions?
So is it a good practice to write everything in a single pass? So, you explain.
Like it's generally a good practice the performance savings not come from just having a single pass, but just having a single pass to render everything and just not really using that data anywhere else and not chain these things together. So that's a pretty latent data dependencies, and it especially worsens if you have to use MSAA and like resolve depths as well. So like generally it's pretty cumbersome to resolve depth buffers to the main memory and then use it afterwards because it's not correct anymore.
And this is specifically for our game because we wanted to support a lot of low-end devices, but we are also experimenting with deferred lighting and some more techniques, which we might not use in this game, but yeah, for other purposes. Okay, last question. We are already out of time.
You have mentioned you have created a custom shader graph. So is it you have created a render pipeline or you have created a complete different shader graph tool where you build your shaders in that graph, at top of the shader graph?
We're using the barely modified shader graph package from the SRP, and we just made it so our render pipeline can work with it and generate custom shaders through it. But the tool itself is basically the same. We have just custom shader generators for us.
You have update your render pipeline,
Yeah,
which is compatible with that shader graph, or you created a new shader graph editor itself, or where you can write your own shader, which is compatible with your pipeline only.
We created a custom render pipeline that is compatible with shader graph. So the shader generator is not on the shader graph side, but on the render pipeline side. The shader graph is just a tool to author those. And yeah, we construct all of our shader data on our render pipeline through a common API. So we can pretty much do the same thing in HLSL and the shader graph itself.
Thank you.